This is a video for AQA Further Pure Mathematics. This is Complex Numbers section 3.5, where we're considering the modulus definitions for loci. Well, the first locus I want to consider is one where we have a point z which is moving so that the modulus of z minus z1 is equal to r. z1 is a fixed point on the plane and z is a variable point xy. Well, if we substitute the expression for z1 into the z minus z1, we get the following, where the real part of the number is x minus x1 and the imaginary part is y minus y1. So if we want to calculate the modulus of that, then we can use Pythagoras' theorem, and we get that the modulus is equal to the square root of x minus x1 squared plus y minus y1 squared, and we're told that that has to be equal to r. Well, we can square both of those to get rid of that square root, so that we end up with x minus x1 squared plus y minus y1 squared equals r squared. And of course now we'll recognize that as being a circle centered on x1, y1 with radius r. So that means that we can interpret this modulus z minus z1 as being the distance of z to z1. In other words, this locus is saying that the distance from z minus the distance from z to z1 is fixed and equal to r. So geometrically then we have the idea that this is a circle. Well, now let's consider a specific example of this. So we're asked now to find the set of points for which z minus 3 minus 4i is equal to 5. So the first thing to notice is that the left hand side of that is not quite in the right form, so we need to rearrange it to give us z minus a point, the point being 3 plus 4i, or z minus z1. In other words, in this particular case then, z1 is 3 plus 4i, so we can consider that on the Argand diagram as being at a point 3, 4. So we now have a fixed distance of 5 from this point 3, 4. In other words, it's a circle, center 3, 4, radius 5. And because we know the equation of a circle, we can therefore write that down as x minus 3 squared plus y minus 4 squared is equal to 25. We could use Pythagoras' theorem with the modulus and therefore get the same equation algebraically. Now I want to look at a different type of locus, this time where we have the modulus of z minus z1 equal to the modulus of z minus z2. So remember that we can interpret the modulus of z minus z1 as being the distance from z1. So what we're saying here is that this is a point moving so that its distance from z1 is equal to its distance from z2. In other words, it's the perpendicular bisector of the line joining z1 to z2. So all of those points on the red line are equidistant from z1 and z2. So again, faced with a particular example like this one, the first thing we need to do is to look at the right hand side there and put it into the correct form, so that we get z minus and then negative 3 plus 4i. So we can interpret this then as being a point which moves so that its distance from 3 is equal to its distance from negative 3 plus 4i. So there we are, it's a line equidistance from the 2 points there. In other words, it's the perpendicular bisector of the line joining 3, 0 to negative 3, 4. But we need to know what its equation is. Now we can consider the equation either geometrically or algebraically. So first of all, let's look at a geometric argument then. So we know that we have the perpendicular bisector of this line. So the first thing to do then is to find the centre of that, and we can see that the centre of that point is at 0, 2, and also the gradient of that line, if we calculate that, is negative 2 over 3. Well, the perpendicular bisector must go through that centre point and be of a gradient equal to 3 over 2. So that's using the idea that the gradients multiply together to give us minus 1. We can use therefore the equation of a straight line through a known point with gradient 3 over 2. And that is y minus y1 equal to gradient times x minus x1. That would be our general equation. Of course we can rearrange that to give us y equals 3 over 2x plus 2. We could, for this particular example, we could have used the fact that its gradient is equal to 3 over 2 and we know the intercept. However, in general it's better to use y minus y1 equals gradient times x minus x1. Here x1 happens to be 0. Right, now let's consider the same thing, this time algebraically. So we know that we have the modulus of z minus 3 equal to modulus of z plus 3 minus 4i. So if we let z equal x plus iy, we can substitute that into the above equation and we end up with this. So now we can rearrange that to give us the real parts and the imaginary parts separately. And now we can use Pythagoras' theorem on both sides of that equation to calculate the moduli. Squared the moduli, so we haven't got the square root included there, so we've just got the square of x minus 3 squared plus y squared on the left hand side, and on the right hand side x plus 3 squared plus and then y minus 4 all squared. When we get this expression, we can see there's quite a bit there that we can then cancel out. For example, the x squareds and the y squareds are going to disappear from both sides of the equation. And then we can rearrange this to the equation y equals 3 over 2x plus 2, which is the one that we had before with the geometric argument. Well, that's the end of this video looking at loci using modulus. In the next video, 3.6, we'll look at definitions using the argument.